All right, so here's how ester reacts, right? Number one, we do acid-catalyzed hydrolysis. So basically, this one is a reverse of Fischer esterification. And of course, they are in equilibrium, like mentioned before. So Fischer esterification is in equilibrium. To drive equilibrium forward, we add alcohol as a solvent, right, and remove water as the reaction proceeds, right? Now, to go backward, what do? Well, you have to drive equilibrium to the product side, and you want to cut ester bond to make an carboxylic acid. Add a lot of water, dump water in there, okay? And you can do distillation. Maybe alcohol will come out first, so that helps as well. So drive equilibrium forward. All right. Let's take a look at the mechanism. What is the reverse of Fischer esterification? All right. Ester, you have to protonate it first. It's not that reactive like acid chloride, acid anhydride. So you have to activate it first. So that's what the catalyst is for. Okay. And then now protonation and then nucleophilic attack. So it can react with water now. Once become reactive, deprotonation. Okay. Now we get to tetrahedral intermediate. All right. Now, same thing. So next one, so we have to go to carboxylic acid. Well, let's say we're going to need this oxygen here, OH here, and OH here. So we have to remove the methanol. So methanol comes out. See that? Methanol comes out. All right. If we want to get rid of methanol, what do we have to do with it? Well, we have to protonate it, activate that group. All right. And then you can kick it out by using the lone pair of one of the oxygen of hydroxide. Look like that. And last one, what we have to do? There we go, easy. So you always make a neutral molecule. So you have to deprotonation. Good job, guys. There we go. All right, that's number one. So react with water. That's in acidic solution. You can react with water. Ester can react with water in basic condition. So we add a lot of sodium hydroxide solution. Okay, we call saponification. Here's how it works. Let's take a look. Notice that there are two steps here. Do not add them together. Acid and base together, they just cancel each other out. Neutralization. Do not separate them. That's a reason, and that's a reason why we add the second step here. Add an acid. Watch for it. All right. Sodium hydroxide got a negative charge on oxygen, so it's a strong reagent. React right away. Here we go. Okay. All right. Now we have to remove. So ethanol comes out. So from double bond, and the ethoxide comes out as a leaving group, leaves. Okay. If you use sodium, let's see. Oh, okay, I see. What's going on here? Okay. Well, some of you think so. We mentioned this before, but some of you probably like forget about it. Let's review real quick. So normally we don't really see. Well, we never see an ethoxide leave as a leaving group, right? Ethoxide is not stable, but in this case, it actually leaves, and there are two reasons. Number one, C double bond O. That's a driving force. Okay. Number two, we started out with a reactive nucleophile. Right, with this guy, reactive nucleophile. If you take a look, when your nucleophile, one of them has negative charge. Yeah, so this is a reactive nucleophile. The activation energy is small compared to any other reaction that you start with the neutral molecules. Otherwise, the activation energy is gonna be super high, right? And the reaction doesn't go anywhere, right? Anyway, so my point is the reactants are reactive. The activation energy is small. So ethoxide can leave. This reaction can actually happen. Okay. All right. Now that's what happened, but we're not done yet. So we have an acid right here. We have a base right here. So ethoxide leaves. All right. Can react that. That's why we stop at carboxylate. Okay. And that is the reason why we add the second step. Add an acid at the end. We have to protonate that carboxylate. All right. So the protonation. Ta-da! Get that. Okay. All right. Now, a little bit about saponification, which is a known reaction. Basically, we're making soap, sapon soap, kind of. So in the old time, so I think you've done that in high school. So we have any fatty acid, usually oil, right? Add a base to it, so they hydrolyze. Okay, in the basic condition, and you get soap, something that's slimy, slippery content, the product. All right. Start with the oil, and an oil looks like this. It's a saturated or unsaturated, depends on type of oil, right? So, but we have a fatty acid chain, three of them linked together with a what do we call, is it glycol? I think it's glycol. Double check for me. All right. So 3 carbon and there's an OH each one. Okay. And that's a type of fat. Butter work as well. All right. So we call this butter fat basically. Add 3 molecules of sodium hydroxide. So what does hydroxide do? We go attack at the carbonyl carbon. All right. Reform. You get negative charge first on oxygen. Reform double bond and then cut the ester bond. Okay. And same thing. So 3 of them. So 3 molecules of it. All right. And then you're gonna get that. Here we go. 3 fatty acid chain, right? And we have this glycol right here coming out, right? The fatty acid chain look like this. So the sodium ion, that's a counter ion, right? So it's stuck there too, right? Everything have to be stabilized, right? Have to be neutral. So we have all this, a bunch of these molecules when react a base and an oil together. So what happened here? Well, we have a polar head, highly polar. That's an ionic bond, right? We have hydrophobic tail, which is non-polar. And this is what happened when all these are like come into contact. They stick together like this. They put the polar head outside and the hydrophobic tail inside like that, right? From something called micelle. Maybe you have heard micelle before, right? And here's how micelle works. If you clean, not micelle work. This is how soap works. Okay, if you have like a something that can be cleaned with just water, not soluble in water, like oil on your plate of your dishes, right? So you put soap onto it. The hydrophobic tail will interact with this oil residue on your plate, okay, or on your body, right? When you exercise, when you walk outside, you have oil, right? And from a micelle inside, the outside is still polar, which is soluble in water, right? So basically, the whole micelle thing here just carry the dirt, oily dirt inside and soluble in water. Okay, this is how you clean it. Okay. All right. More reaction of ester. So this one we call aminolysis. Right? Ester can react with water, can react with amine. Okay. Let's see what we got. So none of these 2 reagents are reactive. Right, so we have to add an acid, add a heat into it. And too slow has little use here. It doesn't really do anything. No, of course, you get an theoretically. Is that a word? Yep. Theoretically, you will get amide. You can make amide from an ester, but it just you start out with a non-reactive reagent. You're not going to get a good yield. We will make amide much more efficiently with start out with the acid chloride. Okay, the mechanism just like the hydrolysis of ester. Yeah, you go back there, but in this time we use amine instead. All right, so same mechanism there. Next one.